In this video, we're going to have a brief overview of isometries. Now, an isometry is a transformation in which the image and the pre-image are the same shape and size. So the first isometry we're going to look at is translation. And translation is where I simply take a figure and translate or shift it left, right, up, down, given the algebraic rule. So in this case, I want to shift triangle LIP, and I want to follow this rule where xy maps to x plus 2, y minus 4. And so I can do this one of two ways. I can look at this as saying, okay, this plus 2 is moving right 2, because I'm adding 2 to all the x values. And then this minus 4, subtracting 4 from all the y values, is moving the figure down 4. And so then I could take the coordinates and go right 2 and down 4. And then label it with L prime. Now, to find the coordinate, I could, for each of these pre-image coordinates, add 2 to the x's, and then subtract 4 from each of the y's. And then I would have my image coordinates, which I could then plot. So either way that we want to do it, it would be fine. And so as you see from this triangle, it looks shifted right 2, down 4. Now, we can also express the translation in vector notation, 2, -4, implying the distance and direction of movement. But we also can put the image, or the pre-image and image, into a matrix. And a matrix is essentially an element in math that we use in a lot of higher level math that I can represent a set of data, in this case it's our set of coordinates. That's what we're going to stick with. So my rows would be x and y, and my columns would be the individual points. And so I can simply list the x's for each point for L prime, I prime, and P prime, and then the y's. Or, if I was just given this matrix and then this rule, I could add 2 to each of the x's and subtract 4 from each of the y's, giving me the image matrix. The next isometry we're going to look at are reflections. Now reflections, we have to remember, we are reflecting over a given line. Please note the notation. A capital R subscript with the line of reflection. And so I'm going to take these coordinates and reflect them over the y-axis. You can do this a couple of different ways. We can look and develop our algebraic rules, or we could remember that when we have a reflection, I am going to go an equal distance to the line of reflection away from it. And so in this case, this E is one unit away from the line of reflection, the y-axis. So I'm going to go 1 in the opposite direction to give me E prime. Same for F and G, 2 away, 2 away. Which would give me the reflection of E prime. And now notice, when we do this, the X changes signs while the Y stays the same. So we can think of it in terms of algebraic rules. We don't want to memorize these rules, but we want to conceptually understand those investigations we were doing in class and how they relate. So if I just take the coordinate x, y, positive y, and reflect it over the line y equals x, x and y stay the same. However, I'm on the negative x coordinate plane, or the x-axis, the negative x-axis over here. So a reflection in the y-axis would yield me a negative of opposite x and then y. With the x-axis, again, x and y stay the same. However, now I'm on the y branch of the y-axis, so I go from x to the opposite of y, or negative y in this case. So now if I were to reflect over the line y equals x, now reflecting over the line of y equals x, what we know is it switches the x and y values. And then, of course, reflecting over the line y equals negative x would also switch x and y. However, notice I'm on the negative branches of the x-axis and the y-axis. So not only am I switching, but I'm changing the signs. And in this case, since x and y are positive, I'm saying negative. However, if it's in a different quadrant, it's going to simply just change the sign. So using this kind of logic of the reflections that we did in class, we can develop these algebraic rules to help us map the coordinate geometry examples that we have up here. The last example of an isometry that we are going to do are rotations. Now, notice the difference in notation. In a reflection, it's a capital R subscript with the line of reflection. However, in a rotation, it's a cursive capital R subscript with the point of reflection, in this case, the origin, or O, and then the degree of rotation, in this case, positive 90. So the way I think about this is if I take this XY and I go positive 90 degree rotation, my x and y switch. However, again, I'm on a negative branch of the x. So I map y and opposite x. Likewise, if I go a negative 90, so clockwise, x and y switch. However, now I'm on the negative branch of the y-axis, so an opposite y and x. If I go a full 180, either negative or positive, take this 90-degree turn, or this 90-degree rotation, for example. If I, again, move it another 90, I'm switching x and y. However, notice I'm on the negative branches of both. And so it maps to opposite x, opposite y. So let's look at what that looks like for our figure here. Given triangle RST, if I want to rotate it 90 degrees, I am switching the x and y and then taking the opposite of x. And then when I plot this, I will see the rotation. Make sure I go in the correct direction with the S. And so now I can actually see the rotation of 90 degrees. So the other piece to take into account is when I talk about a rotation of 90 or negative 90, it's important to note what's called coterminal angle. So if I rotate something a negative 90, that's the same as rotating it a positive 270. And those are called coterminal angles. So if I go a negative 90, that's the same as a positive 270, which is important to understand when you're going through these different algebraic rules. And if we give a negative 90 or a 270, we know that it's the opposite, or we know the coterminal angle of 270 would be negative 90, so that would help us with the rotations later on. All right, thanks for watching.